Check it out now, y'all.
nanoHUB-U online instruction.
Welcome back. This is lecture 3 of the 4th week of the material science of rechargeable batteries. Today we're going to start talking about the dendrite formation and rechargeable batteries. This is one of the most controversial topics. There's a lot of work right now being done. So many of the things you will see are very new, some of them you should take with a grain of salt, and some of them you will just see as experimental evidence. Okay, so this is a cell showing you what happens in a battery that actually fails. Okay, this one actually belonged to a laptop, and you can see here the slot where the laptop battery was. There were several batteries, one here, one here, one here, and apparently there was another one here, okay, and another one here. But you can see this one in particular is the one that failed. This one basically caught fire, and you can see the X-ray of that same cell. Okay, you can see in this case the state of voltage of each of them. One of them delivered when it was fully, as it was recharging. Okay, this one had not been charged. These two were apparently overcharged, and this one M1 is the one that failed. Okay, and this one is called its sister cell because it was subjected to the same load as the previous one. You can see it's getting very close to it, but this is the one that actually ended up exploding. Now, what people did, since this one has already failed, in this case Quinn Horn and their group, what they did is they look at what's happening in this cell, okay, and they just cut it open, okay, and what they found is that in the separator, they found these like bushy-like structures that formed. You can see on this side you have the anode, up here you have the cathode, and here you have the separator that is basically trying to insulate electrons from going from the anode to the cathode. And well, back here you have the back contacts through which you expect the electrons to flow and lithium to go through the metal. Okay, so here you have here these bushy structures that form, and actually the thought here is that these dendrites, as they were forming and they were growing, okay, they were the ones responsible for the failure of that cell. What you see here now is a failure, how the batteries, as they were failing, okay, you have these rings that form and how they were crossing the separator. Clearly some transition occurred here, okay, and each charging cycle you can see that formed a different type of ring, okay, and suggesting that there's something going on there, that something specifically, and internally, as that cell, in this specific dendrite, for example, when that cell fails, it's because internally there occur arcing in the cell. Okay, these are very beautiful experiments as Quinn Horn published them in 2007. Okay, and what I find the most interesting is that before that, very few things on that topic at this level have been done. These images were very nicely cross-sectioned. A lot of work was done to try to understand what's going on. And if you look closer in the literature, you will find out that this is not the only type of lithium dendrite morphology that you will find in the cell, but instead you find all sorts of morphologies. In some cases you can see they look very grainy. In other cases they look more like extruded wires. In other cases you can see here they look like extruded wires that actually bundle on top of themselves, forming this well, I don't even know how to call it, this bundle of wires that manage to make a giant macroscopic wire as it's coming out of the system. Okay, and well, in this case what you have here on one side is the lithium base through which that dendrite poked into the electrolyte. So clearly there's some interaction, electrochemical interaction between the lithium substrate and the electrolyte surroundings, and whatever are the local electrochemical conditions, it's impacting on the morphology of the growth. Okay, and because of the complexity of the system, and as we have seen in previous lectures, all the different types of electrolytes that we have, all the stuff that is occurring at the interface, and the different charging and discharging conditions, it can become very complicated to specify what actually happens there. So what I'm going to do on the next slide is show you other types of dendrites as well. In some cases, well, the expectation is that mass comes and deposits here on the tip. But what people have found is that in some cases that does indeed happen. And in this case, you can see how after 56 hours, this dendrite tip is moving from one side to the other one, okay, until you actually induce a short circuit at the very tip of the structure, okay. And these calculations were performed in 2006 by Dolay and others, Dolay and Roswa and others, and you can see how it's very interesting how, as one would expect initially, mass will come, lithium will come and effectively plate the surface of those phases that actually become more favorable. I find very interesting that this other center over here also has it's a lithium growth, but it's just not growing anymore. It's just standing there. So somehow this growth in the middle has taken over the growth of the entire the surroundings of the system. Okay. Now, in this case, Crowther and West observed the same thing, but they also observed, in addition to that they could also see lithium growing from what appeared to be from the base out. Okay, in this case, you have here, in this case, a copper wire that is basically poking out into a flow of lithium salts with electrolyte that is, in this case, coming apparently downwards. And if you look at the frames at the different snapshots, you can see how the dendrite in this case, it nucleates from the corner of the copper wire. And after some time, how that dendrite itself starts to bend on itself. My understanding is that the wall that it's blocking from the flow directly touching this wire ends here. So the moment it sees the wall, it bends, maybe as a result of the flow itself, or maybe as a result that this head actually is extruding lithium from the bottom of the wire. It's not clear why that happens, but this experiment suggests that. Another experiment was performed. In this case, this one was made by Dolay and co-workers, and you can see here you have electrode on one side, the electrode on the other one, and how outside the plane there's nothing, and how that dendrite is poking out and effectively pushing from the bottom towards the rest of the system. Really suggesting that there are at least two mechanisms for growing these dendrites, one by accumulating material on the top, and another one through which it extrudes from the bottom. Not being very clear why that happens. Well, there are other, in this case, more experiments from Crowther and West, and you can see how, if you look locally what's occurring, after 460 seconds you start forming this wavy structure, and how at some point one of these tips takes off, and how ends up being dominating the growth of the entirety of the structure, really suggesting that something occurs here at the tip. There's something different at the tip of this growth that is controlling the morphology of the surroundings. You can see how the back actually just simply stops growing once one spot dominates the growth. It's like if it's shadowing it and it doesn't let it grow anymore. Well, this just shows you the links of what this happens. You know, this cross-section really corresponds to 191 microns. And well, this is just showing you how much charge you have. And the experiments are very, very nice because they not only graphically show you what's occurring with that dendrite, but they're also quantifying the velocity of the tip. In this case, the velocity of the object that is furthest ahead. So you can see how at the beginning it really accelerates as a result of being the dominating object, and then starts to slow down until it reaches a final value. They did this for different compositions, mixtures of electrolyte, different mixtures of PCDMC for a certain amount of salt. And well, in this particular case, for 4 milliamps per centimeter square, you can see how it's really growing very fast. It's really growing about, its peak velocity is basically 1 micrometer per second, which is a lot of lithium being plated in one region. Okay, now, one of the disadvantages of these experiments is the fact that they can only quantify lithium formation the moment their optical microscope is able to see it. If the resolution of the optical microscope cannot resolve that, then they will not see the formation events. So it turns out that that will only occur after you reach a specific critical current density. And well, very recently, in fact, in 2013, Stark, Ding, and Cole basically started quantifying the nucleation of all the different dendrites as they form on in this case, on isolated substrates. And in this case, by controlling the mixtures of, specifying a mixture of ECDMC in LiPF6, you can see how you have different nuclei that forms, in some cases, for very large currents, just after 3 seconds, and after 4 seconds, many of those actually tiny ones disappear, being replaced by very large ones. And well, eventually what you have is that you have this entire surface covered with individual dendrites, and a few of them are the ones that eventually take over the rest of the system, while the other ones don't grow, either remain put or redissolve back in the electrolyte. And in their experiments, what they did is they quantified the number of nuclei per centimeter square as a function of time, suggesting that the number of nuclei basically reaches a limit, suggesting that there's some critical nucleation rate occurring in the system. And now, if what they do, if instead is they add, well, this chemical, what happens is that they stop observing this behavior, and instead they only see very local, isolated drainage formation. And still, you can see this filament-like structures, in some cases surrounded by these tiny structures as well. But always, one of them will take over and dominate the growth of the entire system. And well, as a result of that, you end up having those dendrites. Now, its morphology is such that you would expect that after a few seconds, the addition of that chemical will basically suppress the formation of some of them. And but after some time, if you wait long enough, eventually some of them will form, some critical energy will be overcome, leading to the formation of these nuclei, and eventually controlling their growth and the formation of a specific morphology. This becomes important because it really shows that what chemical you put in the electrolyte, what is the electrolyte initial composition, what is the morphology of the substrate, what is the chemistry of the substrate, and what are the charging and discharging conditions will not only specify whether a dendrite will grow or not, but will also specify the morphology of the dendrite itself. Okay? Now, in this case, what they're doing here is observing the distribution of the chemical that they put in there, and showing that the moment they put it in, it does obviously something to the substrate, but it does it in a non-homogeneous way, inducing with that or favoring with that the formation of some spots with respect to other ones. In fact, what they speculated was that there will be some regions, especially because of the sodium component, that will make the SEI layer to be inhomogeneous, controlling with that the formation of some dendrites. So what they expect is that dendrite actually plays a role the SEI plays a role in interacting with the dendrites. So if you have a nuclei that forms on the surface of a substrate, an SEI forms immediately because this SEI layer is brittle. In some cases, it can break, okay, and that break may lead to the formation of new SEI layer, driving then the growth of that dendrite to be uniformly if the kinetics of the formation of that SEI layer occurs fast. If instead what happens is that you put some chemical that first favors the heterogeneous nucleation of SEI in some regions but not in others, what will happen is that that inhomogeneity of surfacial strength will basically suppress the growth of SEI in some regions and will favor the growth of dendrites in other regions, giving it with that its complex morphology. Okay, and in this case, this is related to the different mechanisms that you will have. And in this case, of course, the thought is that it's growing all from the tip with obstacles imposing an additional twist to the morphology. So what we can say really is that we have really two types of growth occurring in the system. One is where growth occurs from the tip, okay, and the base remains the same. And another one where it's base control, where basically somehow lithium is coming from the bottom of the material, and that induces an electrochemical driving force to extruding it from the base, making the tip remain the same. Somehow, as the tip moves forward, the back of the electrode just pushes in one direction. So now this, of course, is on very controlled experiments on flat surfaces, which, as you know by now, is really very far away to what occurs in a real cell, because in a real cell, what you really have is a whole distribution of particles. So if in this case, Steve Harris, Timmons, Baker, and Monroe, what they did is they basically built such setup, okay, where they put here a glass surface so they can see from the top. In one side, they have an anode, and the other side they had a cathode, and here they have a spacer, okay, and some springs at the bottom to basically support the system. And so really what they have is, on one side they have their carbon electrode made out of particles, on the other side they have a lithium metal electrode, and they just apply a voltage difference between both of them. So lithium basically can plate or can deplate from the metal electrode, diffuse through the electrolyte, and intercalate into the graphite system. And what they found was something very interesting. Okay, what they find is that as lithium proceeds, and noticing that the lithium counter electrode is on the side, lithium is coming and coloring at different rates the anode made out of particles. And even though each of these particles is spherical and roughly the same size and shape, the lithium intercalation does not occur at the same rates. In this case, each color corresponds to a different intercalation state, because it turns out that the color of lithiated graphite actually changes when you impose lithium in it, when you put lithium in it. So in this case, you can see how as the discharge proceeds, the more lithiated particles reach this goldish color, while the less lithiated particles have a reddish color. And even though in between you have these a gold color, some regions are more intense than others as a result of the inhomogeneities of lithiation. Now, if the discharge proceeds and one reaches the solubility limit, what you find is that not at every spot, but in some spots, these silvery regions appear. In this case, this is graphite. This is lithium dendrites that they will just start forming, propagating then through the back of the system. This is, of course, at this level. Okay, if you look at it in much more detail, okay, what you will find, okay, is that these dendrites, and actually this video shows you how the dendrites form. They start as spherical objects, and they don't occur at every spot. They seem to occur only at very specific spots, and they start competing with each other. Some of them will grow, some of them will just stop growing and stay, some of them will start shrinking, and eventually you can see that one of them will dominate the growth of the entire system, taking over the kinetics of the system. So experimentally, what does this tell us? Well, really, because these dendrites don't occur all exactly at the same time, what we actually observe is that actually for a dendrite to form, one would expect an incubation time, a time that one has to wait for this dendrite nuclei to start forming on the surface. These could be something from the order of hours to milliseconds, okay? After sometimes passes, okay, then one would expect that incubation will be followed by early growth, okay? And in this case, it seems that the dendrites, at least in this setup, start to grow as spherical, hemispherical caps, okay? And of course, after this happens, then one of them dominates the process, leading to what we call late growth, which is when the one that dominates basically takes over the whole system and making the other dendrites, surrounding dendrites, to just stay put or to redissolve back into the electrolyte. Okay, this has been really quantified in several. Oh, and by the way, while this might take a few milliseconds, this growth stage could take from hours also to days, right? Depending on what current. Once a dendrite stably grows, it'll just keep growing. Okay, and that also leads to the which one will grow depends on the competition for growth. Basically, which one will dominate. Now, theoretically, how has this been historically described? Well, one expects that the anode develops maybe a morphological instability, and while the electrolyte is coming through, okay, and as that happens, then the bulk diffusion of the species will come and induce electrochemical potential gradients, okay, and those gradients are expected to control the growth of the system. This approach was formulated initially by Chasaviel, okay, and the thought was that the position occurs at the interface. Okay, interaction of the position rate with ion concentration, current density or potential, and surface tension are all occurring, really suggesting that it's not only the macroscopic potential, but what occurs locally in the system. And this other approach where they include the concept of surface tension was proposed by Monroe and Newman. Okay, and when you do that, you really end up having from those two approaches different types of result. Chasaviel's approach really suggests that there is a critical current density, or if you prefer, a critical over potential that will lead to the formation of dendrites, while Monroe assumes something similar, except that as compared to that I star number that they propose, they say in their end, they say it's 0.75 times as large. Okay. Then Chasaviel suggests that there's an incubation time, as we saw from the experiments, that has to occur, while Newman is not concerned about that, or at least doesn't acknowledge it in their paper, and suggests that actually there's some incubation time. That incubation time can really be ignored in comparison to growth. Okay. Chasaviel suggests that the position rate occurs at a velocity that is proportional to the electric field, okay, imposed on the system, and there's some mobility. While in this case, Monroe and Newman suggest that the position rate can be such that it can actually accelerate and make the tip grow faster as it goes. Okay, now you can see both of them have pointed out, and the literature has pointed out at results that support both of them. So there are different types of accounts that depend on the conditions in the system, and so what we will do in the next lecture is try to put by using the equations, common aspects of both of them, using the equations that they both propose, to try to reconcile both approaches and to be able to describe them. Okay, and well, we'll do that on the next lecture. Thank you.